Whenever we have a statistical experiment where the outcomes in it are equally likely, if we want to calculate probabilities for this experiment, then ultimately what we're trying to do is to solve combinatorial style problems. So problems of probability become problems of counting. So when our outcomes are equally likely, probabilities of any event can be found by solving counting problems using techniques from combinatorics. And this makes combinatorics tied quite closely to probability. So what is the equally likely probability model? Well, if we're given a sample space and our outcomes here are going to be listed as S1, S2 up to Sk, so there are k total outcomes from our statistical experiment, then the equally likely probability model is going to assign equal probability, and specifically that probability has to be 1 over k to each of the outcomes. Now, if we take any event from this sample space, so we're taking a subset of the sample space, E, right, so some subset here, then what we can say is that the probability that E happens is going to be the size of E over the size of our sample space, right? That's NE over N. And in this case, using the assumptions that we've set up here, right? If we're taking K here, then this K is our capital N, right? So we can have the notation there. Oftentimes we'll use capital N to denote the total number. If we've assumed it's K, then we could fill in the K there. Okay, so if we want to solve probability questions when the outcomes are equally likely, what we need to be able to do is find NE and to find N. In some settings, this is going to be quite straightforward, but in other times, we're going to need to use sort of complex combinatorial arguments in order to solve for these probabilities. So let's start just going through several examples to work out how this actually works. So we're going to start with a bag where there are 12 marbles. Each of them are numbered, 5 of them are red, and 7 of them are white. Now, if 2 marbles are to be selected at random, what is the probability that they're both red? Okay, and so we need to think about this, right? E is going to be the event that they are both red. And so what we want to find is the number of ways that E can happen divided by the total number of things that can happen. And so we can start with either of these quantities here, right? What is the total number of things that can happen? Well, in this case, right, we have 12 marbles and we're choosing 2 of them at random. And so if you think about this, we're not talking about the order here. We're not talking about any sequencing. What we're saying is that there are 12 marbles. We want to select 2 of them. So N is going to be 12, choose 2. Now, what about NE here? How many ways are there of selecting 2 red marbles? Well, what we say is that there are 5 total red marbles. We want to pick out 2 of them. And so there's going to be 5 choose 2, right? And so what we can ultimately say is that the probability of E based on this has to be 5 choose 2 divided by 12 choose 2. Right? This is what it has to be based on the equally likely probability model here. Okay, and so if we walk through that argument again, right, there are 12 choose 2, which is 66 total pairs of marbles that can be selected. There are 5 choose 2, which is 10 total pairs of just red marbles. And so then 10 out of 66, or 5 out of 33 ways of choosing 2 red marbles out of all of the total ways that we can choose the marbles, right? So the probability is 5 on 33. Now, if 2 marbles are selected at random, what is the probability that 1 is red and 1 is white? So the thing to note first, right, is that our total number has not changed. We're still not considering any order, so the N is still going to be equal to our 66 that we found in part A. But now, if we're thinking about, well, how many ways can the event E happen, right? The event E is going to be, we have 1 red and then 1 white, okay? And it doesn't have to be in that order. And so how can we think about doing this? Well, of the 5 red marbles, we want to choose 1 of them. Of the 7 white marbles, we want to choose 1 of them. And if we multiply those things together, that gives us the number of ways we can choose each of those. And that is ultimately going to equal 35. Okay, but so we can walk through this argument again. Right, there are 12 choose 2, 66 total pairs, just as in part A. 5 choose 1 times 7 choose 1 is 35 pairs of mixed color, so 1 red, 1 white. So 35 out of 66 is our probability there. Right, the probability in the equally likely model, you count up the number of ways the event can happen, you count up the total number of things that can happen, and you divide those 2 together. Part C, if 2 marbles are selected in sequence, what is the probability that the first is red and the second is white? And so here, notice that N is actually going to be changing, right? Because we're no longer thinking about n as being selecting any two marbles. We now have to think about, well, what was the first marble and what was the second marble? And so there are two ways that we could think about doing this. The first is to just apply the product rule for counting here, right? There are 12 ways of picking our first marble. There are 11 ways of picking our second marble. Alternatively, and it will give you the exact same answer, you can notice that we have 12 total items. We want to select out 2 and order them. That's a permutation, right? So it's the permutations with 12 from 2. So then we ask ourselves, okay, well, how many ways can the event E happen, where the event E is that we first select a red and then we select a white? And there are going to be 5 ways of selecting a red on our first draw, right? And then there are going to be 7 ways of selecting a white on our second draw. And so then the probability that E happens is going to be equal to 5 times 7 out of 12 times 11. Right? We take the total number of ways the event can happen, divide that by the total number of things that can happen. So we can walk through this argument. Right? There are 12 permutations with 12 and 2, 132 total sequences of 2 marbles, 5 ways the first marble, 7 ways the second one. So then we have 35 out of 132 as our probability here. Now, if 2 marbles are selected in sequence, what's the probability that they are both white? Again, we have n being the same total as in part C, right? So we're going to have n is going to be 132. But how do we select out our 2 white marbles, right? So the NE here is going to change. In the first marble, we want it to be white. So there's 7 ways that that can happen. And then the second marble, we want to be white as well. But after we've chosen out the first white marble, there's only 6 white marbles that are left in the bag, right? And so then you're going to have 7 times 6 divided by 132. And so again, we can walk through this. 12 permutations with 12 and 2, 132 total sequences, 7 times 6 or 42 ways of having 2 white marbles. So 42 out of 132, which simplifies down to 7 out of 32. So the probability that you select 2 white marbles in a row is going to be 7 out of 32. Part E. Is it more likely, less likely, or equally likely that a sequence of 2 marbles is going to both have red compared to selecting 2 marbles at random without concern for the order? Right? So what are we asking here? Well, we want to get 2 red marbles, and we want to know, is it going to be more likely, less likely, or equally likely if we treat those marbles as a sequence, or if we treat those marbles as being unordered? Okay, so I'd encourage you to think about this a little bit logically before we give the answer here, right? But if we start trying to answer this, there's sort of 2 approaches we can take. We can either try to intuit our way to the answer, or we can do this directly. So how would we go about doing this directly? Well, in the first case, right, we're going to be thinking about say the unordered marbles, right? And in that way, we know that there are 12 choose 2 ways that we can pick out those marbles. And so that's going to give us n. And then there are going to be 5 choose 2 ways of picking out the red marbles. And so that's going to give us NE, right? And so then what we're saying is that the probability of E in the first model is 5 choose 2 out of 12 choose 2. Okay, and so that gives us our first approach here. The second approach is going to be where we consider this in sequence. And here n we know to be the permutations of 12 and 2, right? And then what about NE? Well, there are going to be 2 ways you could think about that. The first is going to be that there are 5 red marbles on your first draw and 4 on your second draw, which gives you your 20. You could also write this out as the permutations of 5 and 2, right? And so then what our probability here is going to be equal to 20 out of, I believe, that our totals from the previous questions were 132, right? So we can write that down there. So the question is, are these 2 probabilities going to be the same or not? And we could calculate them out and see. Now, on the flip side, we can think about this question sort of more broadly as just asking, well, what's the probability that we get 2 marbles, or 2 red marbles rather? Is that actually going to change whether we consider them sequenced or not? And the way to think about that is, could you tell the difference between your sequence? If you get a red marble and then a red marble, is that different than getting a red marble than a red marble? Right? And no, it's exactly the same thing. And so what we know is that these probabilities intuitively should be the same thing, right? It shouldn't matter whether I consider them ordered or not, because the order doesn't actually change anything in this case. And so if you work out those direct probabilities there, you'll actually find that in this case, they're exactly the same thing, right? 5 out of 33 from A. If you simplify 20 out of 132, that's also 5 out of 33. And so intuitively, the scenarios match, but also algebraically, we can show that they match. Now, part F, we have a slightly different scenario here. Is it more likely, less likely, or equally likely that a sequence of 2 marbles will be red then white compared to getting a red and a white marble when selecting 2 at random without concern for the order? And so what's different here? Well, what's different is that the sequencing, red and then white, is actually different than just saying 1 red and 1 white. Because if you just want 1 red and 1 white, right, you can get a red then a white, or you can get a white and then a red. And so intuitively, it's going to be less likely that we get red than white than it will be to get any of red and white, right? Because red then white, we'll consider it here, but white then red is also going to be considered here. And so you should find that these probabilities are actually going to be different. I'd encourage you to calculate them out directly, right? But because there's some chance of white then red, it's not going to have the same in both scenarios. So take a look at some more examples now. We have a fair coin. It's being flipped 10 times in a row. What is the probability that we have exactly 5 heads being observed? Okay, and so here, right, we can think about this as we have our 10 flips, right? And what we want to do is we want to choose 5 of those locations for there to be heads, right? And so we could say, well, we can do 10, choose 2 to pick out which of those, 10, choose 5, which of those 5 locations are going to be heads, right? And then you can think about, well, how many total ways are there of flipping out these 10 coins, right? And so we can work through this probability here, right? There are 2 to the 10 total sequences of 10 flips. We want 5 of the 10 to be heads. And so 10 choose 5 is going to be there. And so 252 out of 1024 is 63 out of 256 will give us the probability that you have exactly 5 heads on 10 flips of a coin. Part B, what's the probability that exactly 3 heads are observed and all heads are observed in a row? Okay, so now we have to start thinking through this one a little bit more carefully, right? And so how can we think about the ways of doing this? Well, one thing that we could think about here is that if you observe 3 heads in a row, right? So you observe heads, 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 then you have your 7 other rolls. Okay? And so in some sense, what we could think about is that really, in our restricted case, there are 8 total things that we want to be organizing. We want to be organizing our 3 heads in a row, and then the 7 other rolls that we do not, or that have to be all of our tails, right? So we have to have 7 tails, 3 heads, and we're going to be placing the 3 heads together. The 7 tails can go around them in any way that you want. Okay, and so then the question sort of becomes, well, we have 8 places to place these things, right? We're going to be placing tails in 7 of them, 3 heads in 1 of them. And if we choose out that one space that we're going to be putting it, that's where we can think about the heads actually going, right? So there are still 1024 total sequences of 10 flips. We want to observe 3 heads and 7 tails, but we can treat the 3 heads as one block. And so there are only 8 items total to place. And so if we have our 8 factorial ways of organizing those tails that we want to put out, right? But then what do we have to do? We have to divide that by 7 factorial. And why are we dividing by 7 factorial? Well, we have 7 heads, right? So what we're thinking about here, right, sort of graphically, I'll try to sketch it over in this area over here, right? So we have our heads, which we're going to group together as 3 heads all as 1, right? And then we have our 7 tails. Okay. And so we want to organize all of these into a line, right? So that's going to give us our 8 factorial ways of putting those all in a line. But these 7 tails here, right, that's going to be 7 factorial ways of organizing those. And of course, if you have a tail as the first one, it doesn't matter which tail is the first one. So that's where we get our 8 factorial over 7 factorial. You could also just do 8 choose 1 here, right? That's going to work too. There are multiple ways of sort of approaching this problem, but in any case, we're going to end up with a total of 8, right? So that's 8 out of 1024, or 1 in 128. Part C, what is the probability that at least 1 tail is observed? And so if you want to know what's the probability that at least 1 tail is observed, right, we could think about this as being, well, the probability that you observe 1 tail, or 2 tails, or 3 tails, or and so forth, up to, or 10 tails, right? That's going to be one way of thinking about it. Anytime you start writing down an event and that event gets really big, you have a bunch of unions, you should immediately start thinking, well, is the complement going to be useful for me here? And one thing that's sort of a dead giveaway that the complement's going to be useful is when we say at least. And at least one in this case is a particularly strong giveaway, right? But saying at least one, right, if we call this event right here the event E, we can ask ourselves, well, what's the event E complement? And the event E complement, if you're at least one is E, then E complement is going to be not at least one, which is to say the event T0. And so what we can say is that the probability of E using our complement rule has to be 1 minus the probability of E complement. And so that's 1 minus the probability that you roll 0 tails. And what are the likelihood that you roll 0 tails? Well, in our situation, right, we know that there are going to be a total number of 1024 sequences of 10 flips. And our question becomes, how many ways are there of rolling 0 tails, right? In other words, we can do our 10 choose 0, right? If you do 10 choose 0, you're going to find that that is exactly 1, right? In other words, we could have done 10 choose 10 and counted up how many ways are there of placing the heads. But so what we can say is that this is going to be 1 minus 1 out of 1024. Okay, and so let's walk through that again, the argument here. But here, thinking through the complement is always going to make our lives quite a lot more straightforward. Okay, so E can be thought of as the complement to no tails being observed. So the complement rule tells us the probability of E is 1 minus the probability of E complement. The only way that no tails are observed is if you have all heads, right? There's exactly one sequence that does that. And so then the probability of E is 1 minus the probability of E complement. So that's 1 minus 1 out of 1024, or 1023 out of 1024. In part D, what is the probability that at least 2 tails are observed? Okay, and so again, we're going to use the same logic that we used for part C, but instead of us just thinking, well, it's going to be the complement of 0 tails, here we have to have the complement of 0 tails or 1 tails. Right? And so I'd encourage you to work through this probability yourself and see if you can work it out. But what we're going to say is that the probability of E is going to be 1 minus the probability of E complement. And what is E complement here? Well, that's the probability, or that's the event that you observe 0 tails or that you observe 1 tail, right? And so this here is 1 minus the probability that you observe 0 tails plus the probability that you observe 1 tail. And the reason we can split that up is because of additivity, right? T0 and T1 are mutually exclusive events. And so then we can work this out, right? We already found what T0 was, the probability of T0 in the previous question up here. Okay, and so then we just need to work out the probability of T1 and walk through the same type of process here. Okay, so 1 minus E0 minus E1. So probability of E0 was 1 out of 1024. The size of E1, we need to select one place for a tail to go. So that's 10 choose 1 ways that that can happen. So the probability of E1 is 10 out of 1024. Right? And so then the probability of E is 1 minus 1 out of 1024 minus 10 out of 1024, which is 1013 out of 1024. Right? And so if we have the probability of observing at least 2 tails, then we can do the same thing here. Okay, so at least is still a giveaway that maybe the complement is going to be useful for us. If we look at another example here, right, we have a factory. They're producing batches of 100 widgets. Some of these widgets might be defective. Now, for quality control, a sample is going to be tested, and if any defective widgets are found, the batch is rejected. Suppose that one batch has a total of 8 defective widgets in it, right? So we have 100 total widgets, 8 of them are defective. If we take a sample of size 5, what is the probability that the batch is going to be rejected? And so we have to think about here, E is going to be the probability or the event that we reject the batch. Okay. And what we want to know is we want the probability of E, right, which is the number of ways that E can happen divided by the total number of things that can happen. Well, what we're doing is we have a sample of, or we have a total of 100 widgets, and we're taking out a sample of 5 of them, right? And so we take 100, choose 5 as our total number. And then what we want to figure out is, okay, well, how many ways are there of E happening here? Okay, and so E happening would mean that we have at least one defective widget. Now, there's that phrase again, right? At least one. And so instead of us calculating PE directly, what we can instead think about is, well, what would be happening with EC? So this is do not reject, right? For the complement of E. And so we know that PE can be linked through the probability of E complement. And why is that easier? Well, if we think about, well, what's the probability of E complement? That's going to be the number of ways that E complement can happen out of the total number of things that can happen. We already know the total number of things that can happen. And in order for E complement to happen, we need to have not selected any of the defective widgets, right? So we have 8 defective widgets. We have 100 total, right? And so if you take 100 minus 8, that gives you 92 non-defective widgets, right? So 92, choose 5 of them is going to equal the number of ways that E complement can happen. Okay, and so then E complement becomes something that is easy to directly calculate. If you wanted to get an E here, then you're going to have to be thinking about, well, how many ways can you do one defective widget? How many ways can you do 2? How many ways can you do 3? How many ways can you do 4? And how many ways can you do 5? Right, so again, here, as soon as we start trying to solve this problem, it makes us think that, okay, the complement is probably going to be easier for us to work through. So walking through this argument, there are going to be 100 choose 5 ways of taking our total sample. There are 100 minus 8, that's the 92, choose 5, that have no defective widgets in them. So then the probability that we have, that we reject the sample is going to be 1 minus the ratio of those two quantities, which gives us about 35%, right? So there's about a 35% chance that the batch is rejected. How would this change if we do a sample of size 10? What is the probability that the batch ends up being rejected here? Okay, and so we can work through the exact same process, except instead of us taking a sample of size 5, we're now taking a sample of size 10, right? So we're going to use 100 minus 8, choose 10. We're going to use 100, choose 10 as our denominator, right? And so this gives us the probability that we get 0 defective widgets, 1 minus that because we want the probability of the batch being rejected, and that brings us up to a probability of about 58%. So in the case of taking a sample of size 10, there's about a 58% chance that we would reject this batch. To take one final sort of example here, we can think about what we call the birthday problem. So to set up the birthday problem, suppose that an equal number of individuals are born on every day of the year. We'll ignore February 29th. So there are 365 days in the year. The question that we want to answer is, how large of a group do you require in order to have a greater than 50% chance that any two individuals end up sharing a birthday? I'd encourage you to first think about this problem just intuitively. What does your intuition tell you in terms of solving this birthday problem here? I'd then encourage you to try to actually work this out for yourself, right? To work through this problem using the techniques we've been using throughout here in this equally likely probability model, right? So we can assume every birthday is equally likely. There are 365 different birthdays. We're going to have different people coming into the room with different birthdays, and we want to know what's the probability that any two of them share a birthday. Okay, then we'll work through this whole problem itself. But again, thinking through this intuitively, if you're like most people are going to put a pretty high number up in order to get a 50% chance. Most people are going to think that this number is probably somewhere around 180, right? Because there are 365 days. Half of that is around 180, right? So that's perhaps what people are going to think. You know, some people also might think, well, it's not going to be that high. It's not going to be 50% of them. And so, you know, maybe we could drop down to 100, or maybe we could drop down to 50. And so intuitively, let's try to gauge where you're at. But then again, let's work through this all very formally. So suppose that we have k individuals in the group. What's the probability that in a group of k individuals, at least 2 people are going to share a birthday? We can solve this problem directly. And so how can we solve this problem directly? Well, the first thing to ask is, how many different sets of birthdays are there going to be for these k individuals? Okay, and so if we wanted to work out the different sets of birthdays for them, right, we could talk about there being 365 possibilities for each of the k people, right? And you could do 365 to the power of k. That's going to be easy enough. But then we would have to have this framing here of at least 2, right? So we're saying at least 2 again. And so we could say, if there's k people in this group, well, we could have 2 people sharing a birthday, but then we could have 3 people or 4 people or 5 people or 6 people or whatever else. And maybe they're paired off, and maybe, you have 2 groups of 2 and then a group of 5, right? It becomes really complex. So instead, we're going to try to think about the complement. So we're going to answer, well, what's the probability that no one shares a birthday? Because in order for no one to share a birthday, everyone has to have a unique birthday. So that becomes a much easier question for us to address here, right? So we can say the probability of E is 1 minus the probability of E complement, where E complements the probability that no one shares a birthday. If K people are in the room, there are 365 to the power of K possible sequences of birthdays. So person 1 has a birthday, person 2 has a birthday, and so forth, okay? Now, if you wanted to have how many ways can we pick out a unique sequence of birthdays, right? Then what we're doing is a permutation without replacement, right? For the total possibilities, we're doing permutations with replacement. But if everyone has to have a different birthday, there are 365 birthdays for us to pick, and we want to pick out K of those in order for those to be all different. And so the number of ways that you can have K different birthdays in a room here is going to be 365, or permutations with 365 total, and K items being selected. And so then the probability that E occurs is 1 minus this 365 over 365 minus K factorial divided by our total number here, which we can write in the denominator as 365 to the power of K. Okay, and so the probability here is going to be this expression. Now, this hasn't answered the original birthday problem, but this is going to be valid no matter what value of K we plug in here. And so we could plug in different values of K and start to check. However, we could also just say, well, what's the value of K that is going to make this greater than or equal to 25? And if you solve that out, what you find is that you need K to be greater than or equal to 23. Okay? So if there are 23 people in a room, there is a 50.7% chance that at least 2 people share a birthday. To say again, with 23 people in a room, there is a better chance that at least 2 people share a birthday than that no one shares a birthday. Okay? Now, I don't know about you, but again, my intuition on this problem is not that the number would be as low as 23. That feels really low to me. But if you work through the probabilities, this has to be the case. Of course, in the real world, not all birthdays are going to be equally likely. There might be other factors at play, but this is still going to be a fairly good approximation to the true problem here. Okay, so the reason that this is such a low thing is because we're not asking what's the probability that a specific pair of people share a birthday. We're also not asking what's the probability that anyone shares your specific birthday. Those are all far lower probabilities. But if you start to think about, okay, you have 23 people in a room, and how many ways could you make out groups of 2, or how many ways could you make out groups of 3, or how many ways could you make out groups of 4, you start to realize that there's a lot of different possible subgroups there. And that's why that probability can get so large so quickly. Okay, so if you have a room that has 50 people in it instead, the probability is 97%, or roughly 97%, that at least 2 people share a birthday. If you have 100 people in a room, then you're looking at 99.99999%. There's almost a certainty that in a room of 100 people, at least 2 of them are going to share a birthday. Right? And so what that means for you is if you're ever in a room and there's 23 other people there, probably there are going to be 2 people in that room who actually share a birthday. Now, some words of warning for dealing with these types of probabilities. While the equally likely probability model applies in many situations, it's not always going to be the probability model that's relevant. So, for instance, if you consider rolling a sum of 7 when you're rolling 2 fair 6-sided dice, right? If you consider the sums on the dice, we're no longer dealing with an equally likely probability model, right? 7s are more likely than 2s or than 12s, okay? So in many settings, certain outcomes might be more or less probable. And so if you're in a case where there's more or less probability assigned to certain settings, then we can't just rely on combinatorics to give us our probabilities. It's no longer the case that you can count up the number of ways the event happens, the total number of things that happens, and divide those two things. If everything's equally likely, that's exactly what we do. If things aren't equally likely, then we have to use other techniques. So another point is that solving combinatorics problems does require practice. Right? So the solutions are often easier to read through than they are to derive. And so I would encourage you, anytime you're faced with an example, try the problem out for yourself. See how you might approach it. There's oftentimes going to be very many different approaches that you could take to getting to the right answer. But unless you start to develop that intuition for yourself, these problems are going to remain very challenging. Once you're comfortable with the basic tools, once you know what a combination is and a permutation and a factorial are, right, then it's important to start pulling them all together into real problems. And so then you start to look at the problems, think about how you can count up everything. Because at the end of the day, if you're in the equally likely probability model, you need to count the total number of ways the event can happen. You need to count the total number of things that can happen. And if you can count both of those things, you get your probability out of it for free. If you want places where you can start to investigate these, games of chance are going to be a really great way of doing this, right? And so you could, for instance, think about counting up the ways that the hands in poker apply, right? So that's going to be a rich source of combinatorial problems, and it's something that I would advise you to do, especially if any of this is not clear to you. Now, the axioms of probability and the secondary properties of probability still apply, right? We saw that with the complement rule, but it's also going to apply with additivity or with our general unions or anything else that you might use from there, right? So just because we're working with equally likely probabilities doesn't mean that we should try to directly compute the probability. If we had tried to directly compute the probability of sharing birthdays, that would have been almost impossible to do. Computing the complement is something that is very feasible, right? And so it's important to remember all of the properties of probability are going to apply. We just can then calculate the probabilities using combinatorics directly. Okay. So if you are wanting some examples to work on, what is the probability that you're dealt a pair or a straight in a card game, right? So you think about being dealt out cards. What's the probability that two of them match? What's the probability that you end up with a flush or with a straight, right? You can start to work out these probabilities. You'll need to use the axioms of probability. You'll need to use combinatorics. You'll need to use the equally likely probability model, and it will all come together. And the good thing is that all of these are very well studied, and so you'll be able to find your solutions to these sort of all over the place. They're not hard to work through, but I'd encourage you to practice those yourself. And if you can go through and given any poker hand, you can work out the probabilities there, you're in a really good spot for using the equally likely probability model. Okay. So to calculate any probabilities under the assumption of equally likely outcomes, tools from combinatorics need to be used. These tools will be combined with axioms and the principles of probability in order to actually work through our different probability rules here. Right? But ultimately, we're going to still be relying on the fundamentals of probability. So the equally likely probability model comes up very often. It's not the only probability model that's going to be relevant, but it is sufficiently relevant that it's worth studying in its own regard.